Right. Welcome to 2.1 notes. 2.1 is the start of our module on logic. Okay. And the first thing about logic we're going to talk about is inductive reasoning. Now, this is going to be very different from other, modules in Algebra 1 and even geometry, because this module is going to be very focused on explaining things and having good reasoning skills. Okay. Not a lot of algebra is going to be happening or like solving equations. It's going to be more like explaining what you see. Okay. And having good logic to back up your findings. So first definition is inductive reasoning. Inductive reasoning is making a conclusion based on observations and patterns. So this this doesn't have to be with math. You can use inductive reasoning for many things like weather, traffic, that kind of stuff. Where when you notice patterns, or like with traffic, like I know at certain times, certain roads are gonna be busier than at different times. Okay, so you're making conclusions based on observations and just patterns that you notice. But today we're going to be looking at mainly using this with math, okay, and numbers. And then that conclusion you make from inductive reasoning is a conjecture, a concluding statement reached by using inductive reasoning. So for number one, we're going to do a couple of these, okay? So we're going to find the next 5 terms and then write a conjecture. So I try and notice what pattern I'm noticing here. So they went from 38 to 31, then to 24 to 17. So I'm kind of noticing that they're going down by 7, right? Each time they're going down by 7. So I would just assume, I'm going to use my inductive skills to assume that, we're going to go down 7 again, okay, which gets us 10. And if you go down 7 from 10, you get 3, okay? And then if you go down 7 from 3, you get negative 4, then negative 11, then negative 18, okay? Now, our conjecture, and I already wrote it down, it's just down here. I'm going to just slide it over here. I can get to it. My conjecture I made, okay, and this is how you want to write most of your conjectures, okay, use complete sentences, and your conjecture is about how we generate the next term. So how we generate the next 5 terms is to generate the next term, subtract 7 from the previous term, okay? So that would be my conjecture, okay, to generate the next term, subtract 7 from the previous term. Now, I want you guys to try. I'll give you guys a minute, and you can pause right now. So pause right now and try to figure out the pattern that's going on with number 2. I'll give you guys a second. So hopefully you tried it, okay? You paused it, you tried, before I just give it away. But the pattern that I notice, okay, is if you look at 2 and 5, notice that to go from 2 to 5, yeah, you're adding 3, but it's not going to be like you're adding 3 for each of these, so I don't want that to be my conjecture because, we're not adding 3 each time. It's different than that. We're actually doubling the number. So to go from 2 to 5, we're doing 2 times 2. We're doubling 2 plus 1. Okay? Again, to go from 511, we're going from 2, and then we're doubling 5, right? So we're going to do 2 times 5 plus 1. And you notice 2 times 5 plus 1 gets you 11, okay? And then to get to 23, we're going to double 11. We're going to double 11. So if you double 11 plus 1, you get 23, because you get 22 plus 1, which is 23. Okay, so if I want to find the next term, okay, we're going to do 2 times 23 plus 1. Okay, 2 times 23 plus 1, that gets us 47. Okay, and now we're going to double 47. So multiply 47 by 2 plus 1. 2 times 47 plus 1 is 95. Okay, and the remaining ones I'll just kind of give you guys, but all we're doing is we're doubling, and then we're adding 1. So if you double 95 and add 1, you get 191, and then 383, and then 767. Okay, so that's my pattern. And then how I can write this in a sentence, like my conjecture, my conclusion statement about how I generate my next term, is to generate the next term, double the previous term and add 1. Okay? Now, you couldn't have came up with a different conjecture, and you could have got the same numbers. Conjectures, they don't have to be the same, okay? You can come up with a different conjecture. If you came up with a different one, that's great. There's different types of conjectures. I like this one the best, though, but if you came up with a different one, I kind of came up with a different one too, but it was a little bit more confusing, so I just kept it like this one. Now, the last one we're going to do on this page, number 3, is this pattern, 1, 4, 9, 16. You should notice that each of these, let's kind of write what I notice about each of these. So 1 is 1 squared. Notice 4 is 2 squared. 3 squared. 4 squared is 16. Each of these are perfect squares. You should have noticed probably right away, if you're good with noticing your perfect squares, that each of these are perfect squares. So the next one's going to be 5 squared, which is 25. Okay. 6 squared, which is 36. 7 squared is going to be the next term, 49. Okay, and then we have 8 squared and 9 squared. So 64 and 81. Okay, so the pattern that I'm noticing, my conjecture, is that each term is a perfect square. And it just goes down the list of perfect squares. Okay, so let's kind of write down that statement I wrote. So my conjecture was that each term is a perfect square. And I said to find the nth. Oh, I should fix this. Should say the nth term. So if I want to find the nth term, square n. So what I mean by the nth term is nth just means any number. So let's say I want to find the 12th term. That would be my nth term, my 12th term. If I want to find my 12th term, I would square 12. So for example, let's just say I want to find my 12th term. Okay, we know it's going to be 12 squared, so it's going to be 144. Okay, so if I want to find my nth term, any term, all I'm going to do is I'm just going to do n squared. So it's just always going to be n squared. Okay. So that's where the nth term comes from. It just means any number. And the reason why in number 3 I use the nth term instead of a previous term, because it says like to generate the next term we use the previous term. Notice that in number 3 we don't use the previous terms to generate our terms. We use the current term. So that's why we don't say. it's a little bit different because we're not using the previous terms to generate our terms. Okay, so I know that might be a little bit new. You might not have seen the nth term before, but that just means any number. Okay, so now moving on to the next page. And you can work for 4, 5, and 6 if you want more practice. But we're going to kind of move on to the next page, which is counterexamples. Now, conjecture, like I said on the first page, is that conclusion you make from inductive reasoning. Now, on the first page, most of our conjectures were true, okay? I don't think we made any false conjectures, but sometimes they can be false, okay? It's more like a hypothesis where, it could be false, it could be true, okay? So, some counterexamples can be false, so let's kind of figure out if one's false. And a counterexample is an example that shows a conjecture is false, so we'll be giving counterexamples if one of these are false. Okay, so we're going to say it's true or false, and then if it's false, we're going to give a counterexample. And I normally like just giving a couple examples to figure out if it's true or false. So for example, for number 7, the sum of any two consecutive integers is always odd. Consecutive means next to, okay? So just two numbers that are next to each other. So we can think like 4 and 5. So if we do 4 plus 5, they're consecutive, we get 9. Notice that 9 is odd, so this is true so far. Let's do another example. Let's do like bigger numbers. Let's do like 100 plus 101. Okay, we get 201, which is also odd. And what you run into is when you're adding an even and odd number, you're always going to get an odd number no matter what two numbers you add, because consecutive means even, then you're adding an odd number, okay? So whenever you do an even plus an odd, you're always going to get odd. So this is a true statement. There is no counterexample because it's true. Okay, number 8. A product of two numbers is always larger than either number. So product means multiply. So it says if you multiply two numbers, that number that you get will always be larger. And this is actually going to be false. Okay, and I'll give it a counterexample. Okay, my counterexample is going to be 2 times 0. Okay, 2 times 0, you get 0. Now, is 0 larger than 2? No. Notice that 0 is not larger than 2. Okay, so this would be my counterexample because it says the product of two numbers is always larger than either number, and 0 is not larger than 2, so this would be false. Okay, so that would be my counterexample for that problem. Okay. It's saying I misspelled false, but it's just my handwriting's so bad. Okay, now I don't even know what happened to my false. Let me fix this. Alright. So, moving on to number 9. The product of two perfect squares is always a perfect square. So let's see. Let's use some examples to figure out if this is true or false. Because to be honest, when I was first doing this, I wasn't even sure if this was true or false. I need to think about it. So if we do 9 times, let's do 9 times 16 first. Let's do that example. Let's do 9 times, oops. And remember, perfect squares are what's on the first page. Okay, perfect squares, like 1, 4, 16, 25, 36. All of those are perfect squares, okay? So I'm going to just multiply any two of them. I'm going to pick 9 and 16. Okay, so I'm going to do 9 times 16. And I got 144, which checks out. 144 is a perfect square. That's 12 squared. So that works. But just because one example is true does not mean the whole statement's true. It has to be true for every single example. And obviously you can't check every single example, but we can check enough to kind of know it's true or false, okay? So let's do a couple more. Let's do 49 times 64. 49 times 64 gets you 3,136. And that's a perfect square. That's a square of 56. This is the same thing as 56 squared. Okay. Now I just picked two random perfect squares and I got a perfect square twice. Okay. So I'm assuming this is true, and this is actually a true statement. Okay. Now you don't have to give examples if it's true. Okay. You only need to give a counterexample if it's false, like on homework or like on a test or anything like that. But I do like just going for examples no matter what, just so I can make sure it's true. Number 10, the area of a rectangle is 6 meters squared. Then the dimensions must be 2 by 3. Okay, this is false. Okay, my counterexample would be a rectangle that's a 1 meter by 6 meter. Okay. And remember, area is just length times width. So if I do 1 times 6, I get, an area of 6 meters squared. So that's obviously going to be false. Let's do 2 more. Let's go to 12. 12 says vertical angles are never complementary angles. This is also going to be false. Okay, and this one, I'm going to give a counterexample using a picture. So it says vertical angles are never complementary. Remember, complementary means they add up to 90. So if I can show that two vertical angles add up to 90, then it would be, we know this would be a false statement. Now, remember, vertical angles are congruent. That's what we learned last week. So let's kind of draw vertical angles. Okay, so, and if I make both of these 45 degrees, okay, notice they're vertical, they're across, and if I add them, I'm getting 90 degrees. Okay, so that's my counterexample. If I add two 45-degree angles, I'm getting 90 degrees. And then let's do like a more fun example. Number 15 says all state names have at least 2 syllables. So a counterexample, if there was one, would be a state with only 1 syllable, because that would make this statement false. Okay, so we need to figure out, is there any states that have 1 syllable? And I can give a counterexample. Okay, that would be Maine. Okay, Maine only has 1 syllable. Okay, so that is my counterexample, Maine. I don't know if there's any other states that only have 1 syllable. That's the one I found. You can maybe look for yourself if you can find a different counterexample. But yeah, counterexamples shows a conjecture is false. So it's just, you're given a conjecture. If you know it's false, give an example of why it's false, and that would be your counterexample of proving it's false. Now, to show a conjecture is true is really actually difficult. And we'll be showing how we can prove conjectures later in the chapter, okay? But for now, you don't have to give an example if it's true. You really only have to give one if it's false. So if you have any questions, you can email me. I'll also be able to answer questions on Monday when I'm back at school, okay? So have a good weekend. I'll see you guys.